Right, so it is time to begin the lecture. The department is privileged to have Professor Raghunathan agreed to give a series of lectures on compact Lie group and their representations. Today is the first class. This course will roughly run for about 8 classes. So I hope you all take interest. From what Jugal just said, there may be a lot of people online, I see, and I think there will be no question answered during the lecture, but people can send their questions on chat, and Dibyendu will look at the chat box. Once in a while, he will request Professor Raghunathan to respond to them.
Thank you. I'm happy to be here to give these lectures on a topic which is a great favorite of mine. It's actually a subject which is more or less finished. I mean, it's everything that can be said about representation theory of compact groups has been said and said a long time ago. But it's the beginning of a whole new chapter, namely harmonic analysis on non-compact Lie groups. And this year happens to be the centenary year of Harishchandra, who was the greatest contributor to that area, to harmonic analysis on non-compact semi-simple groups. So I'm doubly happy for that reason to give this course of lectures. And this is basic material which anyone who wants to do advanced harmonic analysis on semi-simple groups, or number theory for that matter, which has now been related to representation theory in a big way thanks to the program of Langlands, and anybody who wants that must have this background absolutely as essential. Okay, what am I going to start with? I'll first tell you a few things about this so-called Pater-Weil theorem. That's where I'll begin, but I will be very brief and not say too much about it. This is in some sense a background material which you should pick up. If you don't already know this, you should pick it up. There are lots of good expositions. I'm offhand, I'm not able to tell you where to look for, but you people are experts at looking up through Google, so you will find it easily. And there are other younger people here who can tell you where to look for proofs of theorems of this kind. Well, the Pater-Weil theorem is a theorem about harmonic analysis on general compact groups. Harmonic analysis is essentially studying representation theory, unitary representation theory of compact groups. The theorem is comprehensive and gives a complete picture of what happens for with representations of compact groups. When you go to compact Lie groups, you can say something more because the structure is richer, and therefore you can say something much more. But when you just look at compact groups, you cannot say more than what the Pater-Weil theorem tells you, which I am going to state now. First, let me introduce, we are interested in representations finite dimensional representations of a compact topological group. I will make a blanket assumption that all groups considered, that means a topological space, the group structure on it, such that the group operations are all continuous. And I am going to assume the group I am looking at is compact. So that is representations rho, homomorphisms rho of G. Let me give a name to the compact group, topological group G. G to JLN C. in a complex vector space, finite dimensional complex representations. Rho G to JL and C, which is continuous, rho continuous homomorphism. Or I will, instead of specifying JL and C, I will say GLV rho, V rho, a finite dimensional vector space over C. By choosing a basis, you can identify this GLV rho as JL and C. This is linear, C linear automorphisms. It's isomorphic to so that's what a linear representation is. And an important tool for studying representations of compact groups is Haar measure. G, it is known, carries a Borel measure, well, to avoid unnecessary complications, we will always assume that G is has a countable base for topology. You don't have to make this assumption, but if you drop the assumption, every time you will have to say something more, which is a bit of a nuisance, which is why I am avoiding it. Now, G carries the Borel measure mu such that, so it is is invariant under both left and right translations. Mu of G E equals mu of E, mu of E G for every Borel set E and every G in G. That is, the measure is both left and right translation invariant. You have in the case of the real line, for instance, the obvious Lebesgue measure, which is both right and left invariant. The Lebesgue measure is more than a Borel measure, but anyway, you have a Borel measure, and of course you can complete it as you do with Lebesgue measure. The important point is there is a Borel measure mu, which is both left and right translation invariant. This is actually true for locally compact groups, that there is a left translation invariant measure, but the left and right translation invariant measures may not coincide, which it does in the case of compact groups. Obviously, you have also the fact that mu of G is less than infinity, and we will normalize things in such a way that mu of G is 1. We will have and one of the consequences of the existence of Haar measure is the following fact. If rho G to GLV, V rho, by the way, is called the representation space of rho. If any representation there is an inner product, Hermitian inner product, such that rho G V rho G W equals V W for every V W in V rho. That is, there is an inner product which is left invariant by the action of the group. That is the statement, and it's a easy statement to prove. All that you do is pick any inner product. Let's call it ordinary bracket and define VW as integral rho GV rho GW dg.
Round bracket.
Sorry? Oh, this is the, yeah, thanks. You start with the inner product, which is the ordinary bracket here. Take rho GV, rho GW, that, and take the inner product of these two, that gives you a continuous function on G, and this, and you can integrate it on the whole of G because it's a continuous function on the compact space G, and your Borel mesh is always finite, and so forth. This integral makes sense. So this, it is easy to check, is invariant under rho G. All that you do is you apply rho H, rho H W, rho H V, rho H W here, that puts in rho H G and rho H, sorry, that gives in rho G, rho H V, rho G, rho H W, and then use the invariance of the Haar measure and you're done. Sorry? The Haar measure is unique up to scaling.
So the normalized Haar measure is unique.
Normalized Haar measure is unique, right. Sorry?
The inner product is unique up to a constant. Can you say that?
The inner product? No, not necessarily, because you could have a situation when you have a vector space V and another vector space W, and you have a representation in both rho 1, rho 2, and you can combine the representation, you get a representation direct sum, and in one of them you can choose the inner product is unique up on one of them, even if you assume that it's unique on one, it's only up to scalar, up to scaling, and then you can modify things on the two factors as you like. Okay. What happens is when the representation is irreducible, it turns out that the inner product is unique. Okay. Then, so because of this, the conclusion is that every representation of G is blanket assumption G is a compact group now. Every representation of G is completely is unitary. That is, rho G leaves invariant inner product, which you can take as a standard inner product on Cn, and then the representation is unitary. Something preserving the inner product is a unitary transformation. So every representation of G is unitary, and another consequence, every representation is completely reducible. What does that mean? First, I must first say what representation, when is the representation said to be completely reducible? The representation is irreducible if the only subspaces, vector subspaces stable under rho G are V-rho and impact group in its own right. That's the first example one comes across, if you like. If you look at its representation on Cn, that is irreducible. There is no subspace which is left invariant by the entire unitary group. So that is what irreducibility says, that you have no subspace other than the trivial space and the whole space V-rho, which are stable under the action of the entire group rho G and all of rho G. And then The representation is completely reducible. If it is a direct sum of irreducible representations. What do I mean by direct sum? If you have a representation rho G to GLB rho, and another sigma G to GL V tau, you can get a representation on GL. You can get a define a representation rho direct sum tau from GL, sorry, from G to GL of V rho plus V tau. How do I define this? Rho plus tau of G. This must be a mapping from V rho plus V tau into itself. That's what you want. So apply it on a rho plus tau direct sum tau G on vectors here V W, V in V rho, W in V tau. This is defined simply as rho G of V, comma tau G of W. That's the definition of direct sum. And then it makes sense to talk of direct sum of number of copies, of number of representations. And what we're saying here is that the representation is completely reducible if it's a direct sum of irreducible representations. So every representation is completely reducible. This is the next statement. Why? Start with a representation. Now we know that there's a inner product which is left stable by the group. And suppose you have a subspace which is stable, you can take the orthogonal complement. It will automatically be stable. And you can obviously you can start with something minimal of minimal dimension contained in it, which will be irreducible. And an obvious induction takes over, and then you find everything is a sum of irreducible representations. So that's a consequence of the first statement that every representation is unitary. So every representation is completely reducible. And the third statement I want to make here is a representation rho is determined by its character. What do I mean by its character? If you have representation rho G to GLB rho, the character of rho, often denoted chi rho, chi subscript rho, is the function on G defined by setting for every G in G, chi rho of G equals trace rho G. Rho G is a automorphism of V rho. It makes sense to talk of its trace. It's a matrix. To refer to a base, some basis, it's a matrix, and then you can simply sum of the diagonals. That's what the trace is. And as you know, it's independent of the basis. It's a function which is invariant under inner conjugation on the group GLN. If two matrices are conjugates of each other, then they have the same trace. So chi rho G is such a function. So it's obvious then that chi rho of U G U inverse is chi rho of G for every U in G. Because after all, U G U inverse, trace of that is what you want. Trace of rho U G U inverse is what you want. But that is low u can be pulled out, and then you find the trace of G. So from that it's clear that chi rho G equals chi rho u G inverse. Functions which are invariant under, that is, it's a function, chi rho is a function which is invariant under inner conjugation. Such functions are called class functions. So the statement here is that this is determined by its character. Well, I'm not going to prove that statement. I'm going to take that for granted. It's actually a very general algebraic statement. If you have if take any well, take any algebra A, associative algebra A, and suppose you have a homomorphism of two homomorphisms HA into 2 V prime. Then you can define a function on A by simply looking at A in A going to trace HA, and similarly trace H prime A. These are functions on the ring A, on the algebra A. I'm looking at things over a vector space. It doesn't have to be complex vector, it can be any general thing, doesn't matter. But anyway, I'm looking at the case when A is a C algebra, and you look at this. And then it turns out if these two functions coincide, H and H prime, the modules in V and in V prime, isomorphic, provided they are simple modules. This V becomes a module over A, and so does V prime. If they are both simple modules, that is, modules admitting no submodules, they're both, then this trace HA, this function determines the module. The two modules become isomorphic. More generally, if it's completely reducible, the same thing statement is true. If the modules are completely reducible, if the modules are sum of simple modules, then the same statement is true. And this is a special case of this. In fact, this is, you will find this statement, purely algebraic statement, in the famous book of van der Waals as an exercise under semi-simple rings. But the usual proof given for this is somewhat different, because, but it's interesting because it tells you something more about representations. This is true. The following thing is true. Suppose, let me write 4. A representative function on G is a function of the form G going to rho GV comma alpha, where rho G to GLB rho is a representation. V is a vector in V rho, and alpha is an element in the dual of V rho. Such a function is called a representative function corresponding to the representation rho. And the statement one wants is the following. Once it's all part of the Peter-Weyl theorem. The statement is that the take rho GV, sorry, let F G on G corresponding to irreducible representations rho sigma. Then if rho is not equivalent to sigma, but two representatives are equivalent if the corresponding representative spaces, there is an isomorphism. such that the action on the first one carries over to the action on the second one using, if you use the isomorphs. That's what equivalent representation. Then if rho is not equivalent to sigma, well, integral f g notice, sorry, this is I should say G is a linear combination of functions of the form it's a linear combination of functions of the form to GVW. Each one of these, of course, itself is a representative function, but I won't allow linear combinations, allowing V to vary, alpha to vary, and allow linear combinations. Such a function is called a representative function. And then the statement is that if you have representative functions coming from two inequivalent representations, irreducible inequivalent representations, then their inner product is 0. Notice that the trace is a combination, is a representative function. The chi rho is going to be a representative function because you write it in matrix form, rho in matrix form, then it is rho g vi summed up, where vi is a basis. That's how the trace is obtained. So I'm treating vi also as a element of the dual by using the inner product. Okay, so rho g vi sum up, that's how you get the trace. And the trace is coming from different irreducible representations. This integral is 0, so the two cannot be equal. If they become equal, obviously the representative has to be the same, because if the representatives are not equivalent, we know that the trace of one and the trace of the other are orthogonal to each other as functions. Okay, so this is well, and then finally, sorry. Right. These are called matrix coefficients because if you choose a basis and take V and alpha to belong to a basis and its dual, what you get is something which is called a matrix coefficient because it is the rho G, the ijth entry is what it's going to be. Okay, so
Shivale calls it representative. Shivale calls it representative function, but I think Harishchandra calls it matrix coefficient.
Yeah. Well, Harishchandra came from physics, which is probably why he calls it matrix coefficients. No, Chevalier had the profoundest possible influence on Harishchandra, but not in terms of terminology and not in terms of exposition. Because I must say that both Chevalier and Harishchandra are bad expositors, very difficult to read their papers.
Shivale's book on Lie groups is supposed to be one of the great books.
Yes, but it's not easy to read. Well, I studied Lie groups from that book. I know. I've known other books. At the same as a student, I've read other books which are much pleasanter and easier to read. But no, the difficulties in reading Harishchandra's works or Chevalier's works are of a very different nature. They are both, only common thing is they're both difficult. Okay, now, where do I, the final.
Harishchandra was somehow spiritually Chevalier disciplined, no?
Maybe I'll take time out to tell a few interesting stories now and then. What happened is Harishchandra is, of course, the greatest mathematician to produced by India after Ramanujan. It's a good question. One can still discuss. Maybe he's as great as Ramanujan, or whether he's greater and such things of the kind. That's for future to decide. In any case, Harishchandra started out as a physicist. He studied his physics at Allahabad University, got his master's degree from there, and he was a student of K.S. Krishnan. It turned out that the final examination papers, one of the papers went to C.V. Raman for correction. He scored 100% in that paper. And after he finished his master's degree, K.S. Krishnan suggested that he go work with Baba at the Institute of Science in Bangalore. Homi Baba had just come back from England and had been appointed professor at the Institute of Science, Bangalore, and Harishchandra went to study with him. But after a while, Homi Baba decided that Harishchandra should go work with Dirac. Dirac is one of the great names of the 20th century. Baba recommended Dirac that he take Harishchandra as a student, as a postdoc. He went there to study with Dirac, and it turned out almost as soon as he got there, within a few months, Dirac went to Institute for Advanced Study in Princeton as a visiting professor. And he took his postdoc along with him to Princeton, to the Institute for Advanced Studies, where he went. At that time, Chevalier was visiting at the Princeton University, I think, not the institute, I'm not sure where. He was there, and Harishchandra had got interested in representation theory of Lie groups because physicists were interested. At that time, mathematicians were not greatly interested in representation theory of infinite dimensional representation theory of non-compact groups. It was a peripheral area for mathematicians. But for physicists, the Lorentz group was a big thing, and they were studying representations of Lorentz group, and Harishchandra got interested in that and was working at that. And then he came into contact with Chevalier, from whom he learned the rudiments of Lie algebras, and then he made the big jump to essentially study representation theory of non-compact semi-simple groups in general, using Lie algebraic techniques. And the Lie algebraic techniques largely he learned from basic things he learned from Chevalier, but he developed new techniques which completely astounded the mathematical community. And within 10 years, within a decade, he had proved so many interesting things about it. The area became almost central to mathematics. Representation theory, which was considered somewhat to be in the backwaters of mathematics, mathematics was not greatly interested. But by the mid-50s, with Harishchandra's work, it became very important area in all mathematics. Anyway, so that was a digression. So, yeah, so there was this, what I just now wrote down are called orthogonality relations. Actually, so similar things had been done by Schur for finite groups. And it's only carried over, all that was being done was to be carried over to compact, but not necessarily finite groups. And finally, there are two more statements to be made. One is that if you look at L2 of G, for the measure mu, for the Haar measure mu, that's an infinite dimensional space in general. Unless G is finite, that's going to be infinite dimensional. However, it turns out on this, the group operates by left translation. And since the measure is invariant under left translation, the group action is unitary. It preserves the inner product on L2G. Now it's a Hilbert space, and your inner product unitary transformation still makes sense. And G acts as unitary transformations on L2G mu by left translation. You can also do it by right translation, but the two things are essentially equivalent, because by looking at G inverse left translation by G, and if you want to make the right translation look like it's acting on the left, you'll have to put a G inverse there. That's the kind of thing that happens. Okay, now G axis, then L2G mu breaks up into an orthogonal direct sum of finite dimensional irreducible representations. Moreover, each irreducible representation occurs sorry, I didn't want to erase this, but I have no choice really. So this is actually 5. 4 is the orthogonality relations. So moreover, each irreducible representation occurs exactly as many times as its dimension. In other words, L2 G mu is a orthogonal direct sum. This is the notation I use for direct sum, and I'll put a perp there to show indicates orthogonal direct sum. Dimension V rho times V. Set of inequivalent reducible representations. So it becomes a direct sum of a number of irreducible representation. Each irreducible representation occurs only finitely many times. How many times? Exactly as many times as its dimension.
That set countable.
Sorry?
Set of all equivalent irreducible representations.
Yeah, your Hilbert space is countable. Because my group G, I'm assuming, is second countable. So L2G is countable, so everything is countable. It is precisely to avoid complications of that kind that I made the assumptions countable. So this is how L2G mu decomposes. In general, the problem for a general simple Lie group, which is what Harshnadar solved, is to understand how L2 of G mu decomposes. That's much more complicated. For one thing, the direct sums are not adequate. You need what are known as direct integrals of representations. That is one aspect. And then there are sometimes this irreducible representation actually occurs as sub-representation. When you have a direct integral, you have a continuous family, so you cannot expect. But there may be discrete spots, and then you get actual irreducible representations. And such representations are called discrete representations. It's called discrete representations by discrete series represented by Harishchandra, and he is the first one to examine that in great depth. And he had an elaborate theory starting with that for the entire decomposition level to G mod to G mu. Anyway, so this is for compact groups, this was all done by the 1950s by Hermann Weil. I think died in 57 or 58, something of that kind.
1920s.
Huh?
1920s.
Yeah, but it was all done by 50s is what I'm saying. Hermann Weil was the main man, and he had actually done it in the 40s, sure. But any other additional data, everything was known by the 50s, that's what I'm saying. Before Harishchandra embarked on his mathematics, it was all more or less known. Well, there's one more statement which needs to be made. which is the following 6. The set of all representative functions the vector space spanned by all representative functions these are all is dense in the space of all continuous functions in the topology of uniform convergence. In fact, I can say it's a space spanned by all representative functions of irreducible representations, I could say. This is basically a consequence of the earlier statement 5 and the Stone-Weierstrass theorem, which gives you a criteria of when an algebra of functions is dense in the algebra of all continuous functions on a compact space. So this is basically the Peter-Weil theorem, which gives a almost complete description of how to decompose L2G, and also tells you that these representative functions constitute a dense subset of all continuous functions in the uniform topology. This one already tells you that the span of the representative functions is dense in L2 in L2G mu in the Hilbert space topology. Now they are all continuous functions, so they belong to the subspace of all continuous functions on G, because continuous functions are necessarily bounded and therefore in L2, but it says more, actually it says it's even dense in the uniform topology. This is the general outline of Peter-Weil theory, which clearly is a comprehensive description of all that one wants about L2 of all that one wants about harmonic analysis on a compact group. Now,
maybe you want to say a few words about Fourier series being a very special case of this.
Well, okay, right. He has already said it. You look at, so, well, I've been talking about compact groups without giving a single example. What are examples of compact groups? Let me. Of course, the trivial group is compact, but any finite group is obviously also compact. The first non-finite compact group you come across is the circle. Which is also the unity treble with endpoints identified as a circle group. And what are the irreducible representative circle group? It's an easy exercise to show that every irreducible representation of S1 is of dimension 1 and is of the form e power I theta going to e power I n theta for some integer n And from the theory of Fourier series, you know that you need to, these are the characters. As one dimensional, they are the characters. And you know any two of them are orthogonal to each other if n and m are distinct. And the Fourier series theorems, if you have come across the Fair theorem, tells you that any continuous function can be approximated by means of trigonometric polynomials. And that is a special case of Petrel theorem, because these are the representative functions. And the character, of course, in this case, every represents one dimensional. It's not difficult to prove. It's a good exercise. It's known as Schur's lemma in this particular case. And then your usual theorem, like Fair's theorem, tells you that first of all, you know that Fourier expansions are valid in L2. Every L2 function can be expanded as a Fourier series converging in L2. And then there's also Fair's theorem, which tells you that if you have a continuous function, its Fourier series converges not quite C1 summable, and the C1 sum is the continuous function. Never mind what's C1 summable. There's a slight averaging process which you have to use. The Fourier series itself may not converge, but an averaging process you use, you can make it converge. So these are all special cases. This is a special case of the Petrel theorem. And then, of course, you can form products of S1 cross S1 cross S1. And then once you have this statement for S1, you can also get a similar statement for what are called tori, or product of circles, which is the general theory of multiple Fourier series. Of course, in the case of Fourier series, you're asking more special questions. You're asking whether the series converges. You don't, in the case of compact groups, you are not asking for any series being convergent. You're only saying that the linear combinations is dense. But you can ask such questions, but then it requires more information about how these characters are distributed, how they behave, and so on. Anyway, so that is the special case which you have already come across in some sense. Okay, next. Yeah, all this is general theory about compact groups. We know that the character completely determines the representation. So how do I get hold of characters? Now, to get hold of characters, first of all, you have to know more about the structure of the group. For circle, obviously, you can get down all the characters. But if you have a general compact group, it's not clear how to. A character we know is a class function. That's a function which is invariant under inner conjugation. Unless you have a good set of representatives for the conjugacy classes, you cannot hope to understand what the characters of a irreducible representation is. And for that, one has to have such things right, you have to restrict yourself to more special class of compact groups. And these are the compact D groups which we'll be studying. So let me make the definition of a compact Lie group first. First, a Lie group. Yeah. Well, I don't know how many of you will be familiar with the notion of an analytic manifold, real analytic especially. Maybe I should spend some time telling you what that is. Well, okay, so I will really start talking about compact Lie groups only in the next lecture. This lecture I'll tell you a little more about Lie groups, but I can't go into too much detail because that will take too much time away. First, well, people generally are not familiar with, people are familiar with complex analytic functions, but generally they don't deal with real analytic functions. How does one define real analytic function? The simplest way to define a real analytic function is the following. A function f on an open set U Rn R is real analytic that it's has to be real analytic because it's a function into R, so no complex numbers don't figure here. If for every point U in U there is a neighborhood nu of U in Cn. After all, U is subset of Rn, therefore it's contained in Cn. Nu of U in Cn and an analytic function, complex analytic function say phi U from Nu to C such that when you restrict phi U to U intersection Nu is equal to F. That is, you can locally near a point, the given function can be extended as a complex analytic function into C. In a neighborhood inside Cn, your function is defined only on an open set in Rn, but for every point there's got to be a neighborhood Nu in Cn. Sorry, this should be a nu of U in Cn. Should be a neighborhood Nu of U in Cn. So here is the picture, if you like. On the real line, you're looking at a function on some open interval, say for instance. What you want is at any given point, there must be a neighborhood to this point in the complex plane, such that on this you have a function. On this interval, the function f is defined. Here you want this is the neighborhood which I called Nu, and then I want a function phi U on Nu, which goes into complex numbers, such that when you restrict phi U to this piece, you get back f. That's the definition of a real analytic function. An alternate description, which is often the more useful way of dealing with this, is the following. Alternately, for every U in U, there is a disk in Rn du, open disk du in Rn such that, first of all, ultimately, first I must assume that f is C infinity differentiable, and for every U in U, there is just a disk du in Rn such that the Taylor series du contained in our open set U. Disk du in Rn contain open set. The Taylor series of F is C infinity, so the Taylor series makes sense. Taylor series of F at U converges F on all of du. So function is analytic. First of all, it should be C infinity, and on top of being C infinity, you look at any point, look at the Taylor series, because it's infinity. Taylor series makes sense. Taylor series at that point, it's an infinite series, infinite power series. This should converge to the function f in that entire disk. That is the definition. You can see the two definitions are essentially equivalent, because if you have convergence of this power series in this disk, you will have the convergence also in the complex disk around that, and so that will be a complex analytic function, and you're done. Conversely, if you have complex of the kind we have, then its Taylor series automatically converges. Once you know it's complex analytic, it converges. That's complex analysis for you, and therefore you find that the two definitions are equivalent. Okay. The second definition, you don't have to go outside Rn. You can stay within Rn, which is its advantage. In fact, this is the way, even in the complex case, people are studying complex analytic functions using power series techniques very often. That it has certain advantages over doing it with your usual Cauchy integral formula and so on. Anyhow, so this is the approach devised by Weierstrass, one of the great mathematicians of all time. Weierstrass' approach to analytic functions was through power series. This second definition. So he didn't have to make a distinction between complex and real. He could deal with both simultaneously, which is the main advantage of looking at it from this point of view. Okay, now, so that is what an analytic function on an open set in Euclidean spaces. Now, what happens? Then we have standard results of the following kind. If the set of analytic functions on an open set is an algebra under set of analytic functions, right? It's an algebra over R under addition, multiplication of functions. The second important fact one has is, if you have a function, if you open in Rn, a vector valued function f from U to Rm, this definition is analytic if fi 1 less or I less or 10, because f is a m tuple of functions. The vector valued function is nothing but an m tuple of scalar functions, and each of them is analytic. That's the definition of an analytic function. The reason for making this definition is the following: if f u to Rn, u to Rm is analytic and maps into an open set V in Rm and G, I should use G, let me write H from V to Rp is analytic, then H composed with F is analytic. you have a function from U into Rm, which actually goes into some open set V, let's assume. Then you have the map Fu goes U to V, and from V to Rp is an analytic function. The composition is analytic. Once again, to prove this kind of statement, you just can here you can assume P equal to 1 without any loss of generality, and then it's composition of power series with one with another. And you have to show that if you have convergent power series composed with one, you compose one with another, then you get a convergent power series without reference to complex analytics. If you work with complex, the other definition, see, you know that composition of complex analytic functions is complex analytic. You're done. Anyhow, that is what these are two important facts about analytic functions. Now, once you have these facts, I can define the notion of a analytic manifold. First, a topological manifold, by definition, is a space. It's a topological space in which every point has an open neighborhood homeomorphic to an open set in Euclidean space. The Hausdorff topological space such that every point P in M as a neighborhood, as an open neighborhood, U homeomorphic an open set Rn. The Hausdorff topological space is topological N manifold. Is by definition a topological space in which every point is a neighborhood which is homeomorphic to open set in Euclidean N space. For example, look at the sphere. Take any point on the sphere. Take a bit like that and project down. This is the xy plane here and z-axis. So you get a homeomorphism of this portion, this portion. So every point has a neighborhood which is homeomorphic. Yes. Sorry? At this point I don't assume, but yes, eventually yes. all the decent spaces are going to be second countable. So this is an obvious example of a manifold, the sphere, which you intuitively see that every point has a neighborhood. You can actually get a homomorphism like this. So fix a topological manifold, a chart or coordinate chart on a N manifold. Here, one important point is that the number N is completely determined the topology of M. The reason is that an open set in Rn can be homeomorphic to an open set in Rm only if M equals N. That's known as, it's a theorem of L. J. Brouwer, known as invariance of domain. An open set in Rn cannot be homeomorphic to an open set in Rm if M is not equal to N. is obvious in the case of look at the real line, look at an open set in R. It cannot be homeomorphic to open set in any higher dimensional Rn, because in R, you omit a point, the thing gets disconnected. But if you take a disk, omit a point, doesn't get disconnected. So an open set in Rn cannot be homeomorphic to but go beyond dimension 1, it's a deep theorem due to L.E. J. Brower. That's why I could talk of a n manifold.
Are you assuming the manifold is connected?
Yeah, right.
Because like I have
Right. No, the point is this definition, I don't have to assume it's connected. I'm assuming that every point P is a neighborhood homeomorphic to an open set in Rn. So I don't have to assume it's connected. But if it's connected, of course, it's certainly going to be true. Okay. A chart or coordinate chart on M is a pair UF, U open in M, and F U to FU is a homeomorphism U onto an open set in Rn. For example, in the example like here, take this sphere, this part, that's a chart. I can the same. I may have the same U, but I can have a different chart by projecting on the plane of two other axes. At different points, have different charts. So a chart is nothing but this. Two charts are CK equivalent K integer or infinity or omega. Person should say what this is anyway. CK equivalent if the following thing happens. If look at U intersection V, there is a homeomorphism of this under F into F of U intersection V. Because U intersection V is open in U, F of U intersection V is open in F of U. On the other hand, you can go through G, then you get G of U intersection V, which is again open in G V, and hence in Rn. So here are two open sets in Rn. Now, this F is invertible, and you can go by G. So you get a map here. If you want to look at G composed with F inverse, and you also have a map where F composed with G inverse. I want both these maps to be CK, that is K times continuously differentiable. Then I call, or if it's infinitely differentiable. Then I say the two charts are CK compatible. And C omega is the case when the maps are analytic. If F is a homeomorphism, and you can, these are maps of open sets in Euclidean space into itself, open set in Euclidean space, and you can demand it be analytic. That's what I call C omega. So if G composed with F inverse is of class CK. Then I say the two are CK equivalent. See, sorry. We can CK compatible is the word I should use, not equivalent, compatible. Two charts are compatible, CK compatible. In particular, they're analytically compatible or C omega compatible if these composites are analytic. That's the definition of two charts being compatible. Now, I'll call a next to make yet another definition. A CK atlas on M is a collection of charts on M such that union of UI as I varies over I is the whole of M, and for every ij in I, UI fi, uj fj are CK compatible. So that is, it's covered by a number of open sets, each of which is homomorphic to open set Euclidean space. And you also want that when you go transit from one chart to another, the mapping is class CK. Okay, that's the definition of a CK atlas. And you can say suppose you have two CK atlases on the same manifold. You say the two CK atlases are equivalent if any chart in one of them is CK compatible with every chart in the other, and vice versa. Okay. So two atlases are equivalent if for every I in I, respectively j and j, uj prime fj prime is C for every I in I, ui fi is compatible, CK compatible with all uj prime fj prime. Sure. Now, with all this, I can now make the definition of a CK manifold, in particular analytic manifold, C omega analytic manifold. And an analytic manifold is topological manifold together with an equivalence class of CK compatible, CK equivalent in equivalent class to CK atlases. A CK manifold. Okay, I'll stick to analytic. Same. One can make definition of CK manifold is exactly analogous. So this is what an analytic manifold is. The point in making this that, of course, there is clearly some logical problem there, because you're talking about all atlases and things like kind. It's not serious, because you can think of a chart as only a subset and a map. Set of all subsets makes sense and maps make sense. So that's not a problem. And again, so set of atlases will also make sense, and so equivalence class will make sense. And okay, now why is this elaborate definition? This is what enables you to define analytic functions on an analytic manifold, or more generally CK functions or CK manifold. How do you do it? Suppose you define, first of all, we know that analyticity is a local property. If a function is analytic near every point, then it's going to be analytic in the whole open set. So one would like to define when a function is analytic at a point, near a point. How do I do that? Suppose functions need only be defined near that point, and then how do you do it? You use one of these charts in the atlas. The analytic manifold comes with an atlas. That means it comes with a family of charts. Use one of those charts, and then you get a function on Euclidean space by composing with that neighborhood to that point. Demand that function be analytic. This is well defined because we choose another chart. The two charts are related by analytic transformation. One going from one to the other is an analytic map. So composition of analytic maps is analytic. So you're in good shape. So analytic functions, once again, analytic functions are well defined, and then you can define analytic map into Rn, simply an n tuple of analytic functions, and then you can define analytic map of one manifold into another manifold. How do I do that? Once again, it's a local property. At any given point, the function will take this point into some point in P, choose a chart around that point, and take the inverse images of the open set and work. Then it becomes a function into Euclidean space, because it goes into that chart, and from that chart you can pass on to the Euclidean space by the mapping U Fi. And so you demand that be analytic. It's all whole definition is tailored to make all this is very consistent. Well, you see, all this actually, the basis, the idea of defining things like this comes from the implicit function theorem. When you look at something like, the implicit function theorem, just let me take two variables. You're looking at fxy equals 0. And then if you know that df by dx at some point x naught y naught is not 0, whereas fx naught y naught itself is 0, then at that point, take the locus of the points fxy equal to 0. It contains x naught y naught, and then nearby points, once you have this property, I know that the x coordinate gets determined by the y coordinate. So that gives you the y coordinate completely determines, which means it's a chart. What you have got is a chart on that set fxy equals 0. As you with different points, you'll get different charts. So that's exactly what's happening in this sphere. If you look at x square plus y square equal to 1, at every point xy on x square plus y square equal to 1, you know one of the partial derivatives has been non-zero, because partial derivative take you get 2x 2y, and one of them has to be non-zero if it's going to lie on the circle. So you know that you can use, and sometimes the point may be such that both the x derivative and the y derivative is non-zero, in which case you can express x as a function of y or y as a function of x. So that is the transition from one chart to the other. This is what inspired the definition of a manifold. In fact, basically people were only looking at subsets of Euclidean space of this kind of x y equals 0, and there you had the theorem was available saying that you had a chart at every point and so on. So when you want to make it abstract, that was the inspiration. In some sense, some of these many things in mathematics, the crucial thing is to get the right definition, and then things will fall in place. It's often the case. It's amazing that if you make the right definition, things become very simple. I like to compare it with what they call the cutting the Gordian knot. You probably, I don't know if you people know the story of Alexander the Great. Somebody had tied a rope in a very complicated knot, and it was a challenge for people to come and unknot it, so to speak. Lots of people tried and nobody succeeded. And one day this young fellow Alexander comes along and takes a rope, then picks up a scissors and cuts it off. The knot was called the Gordian knot. So sometimes in mathematics you seem to do that. Things look very complicated, but the thing is to completely get rid of the complication by say doesn't exist. Okay, so I think I should stop. I'm already set my time. Thank you.
Questions on the chat box, we can just respond to them.
Yeah, I can see only one question. Srinath Prasad asked an example of a topological manifold that is not second countable.
That is not?
Second countable.
It's a pathological example. There's a so-called Alexandrov line, which to tell him to look for Alexandrov line, Google for Alexandrov line, and you'll find it. It's not see, these are so-called pathological things and not of particularly interesting things. So people have just this example. You take the line and keep on repeating it. You take the real line and keep on repeating it in some ways with some matching, and then indefinite, uncountably many times. That will do the job. Yeah.
So I come from physics background. So we were calling smooth manifolds.
Smooth is C infinity.
What is the advantage of an analytic manifold over
Well, as the point is this: analytic functions are much more rigid in some sense. Okay, they're not as flexible as C infinity functions. So, in a sense, they make it life more difficult. But nevertheless, the reason for looking at analytic manifolds is most naturally occurring objects, which are manifolds, are analytic. And secondly, it turns out that if you have a C1 manifold, it already carries an analytic structure on it, which is compatible with the C1. So you can take the existence of this analytic structure can be taken advantage of because it's a much more rigid structure. That's otherwise very often C infinity is the ideal thing to work with. It's pleasanter, and especially in the case of real Lie groups, it turns out that if you have a topological manifold, which is also a group, it automatically carries a analytic structure and becomes a Lie group, a unique analytic structure. Yeah. Huh? Where? Is a topological manifold together with an equivalence class of analytic atlas. Oh, atlases. Thanks.
No, I am very happy to see there are 80 participants online.
Sorry?
There were 80 participants
Oh.
online.
Let's see what happens next time.